Hello everybody, welcome back to another video. Today we're going to be solving a very high order problem. Let's get right into it. Okay, so right here we have the derivative of x tetration 4. But I'm sure you're wondering, what does tetration 4 even mean? So let's quickly go over that. When we defined exponentiation in mathematics, we have x squared is equal to x times x. And we define this to be 2 times, just like this. We multiply x times x 2 times, which is where the 2 is incorporated. And likewise, x to the fourth equals x times x times x times x, as you know. That's 4 times. But then when we get into fractional exponents, it gets a little bit weird because we don't have a direct definition. So then we use more complicated mathematics, like then we get to the square root, and all of that comes from there. So when we're defining the tetration, let's take a look. When we do x tetration 3, that means it's x to the x to the x, and in total there are 3 x's, like this. 3, just like that. And then when we do x tetration 4, which is the case for this problem, that's just 4. X to the 4 is equal to x to the x to the x to the x. Now make sure that the logic whenever you're using this is that the parentheses go here, then the parentheses go here, and then it comes like this. It should never, this is not equal to, x tetration 4 is never equal to this. Let me show you. It's never this. You always go from the top to the bottom for exponents. That's how it works. All right, let's go into the solution. So we can use something called logarithmic differentiation to differentiate this beast, but I'll be notating it like this. If you want to, you can use a different notation, but this is what I prefer for simplicity. So what we can do is I want to get rid of this exponent, so let's do ln on both sides. Now, by doing that, we get ln of y, the natural log, is equal to x to the x to the x ln x, because we can take the exponent down by doing natural log. Now, once we do that, there's still a bunch of stuff in the exponent, and those are x's. If those were like standard constants or whatever, I would be fine differentiating this, but since there's still x's, let's differentiate. Well, let's take the log on both sides again. So if we take ln again, what happens? On the left, I get ln of y is equal to ln of x to the x to the x ln x. But we have to remember our rules when it comes to ln. The natural log of xy, if these are all in parentheses, natural log of xy is equal to natural log of x plus natural log of y. And this is a log property, not just natural log. But yeah, if we have two things multiplying as the parameter of natural log, we can separate them as a sum of two natural logs, which is very handy. So in this case, we can say the natural log of y is equal to the natural log of x to the x plus natural log of x. So then we get ln of y is equal to x to the x, because we bring the exponent down, x to the x, natural log of x, plus natural log of x. Now still we aren't done, because we see this x in the exponent right here. So what do we do from here? Do we just take natural log on both sides? Well, let's see what happens. I'll write this in orange. If we do, then we get ln of y is equal to ln of this entire thing, x to the x ln x plus ln x. But you'll notice that we don't have any way of simplifying this further. And because this is a sum of two different terms, we can't just separate this into a sum of logs, meaning we won't be able to bring this exponent down as a coefficient of the natural log, since we're summing here. So we have to find a different approach. Instead of just taking natural log, something wise we should do is move this to the other side. So then when we take natural log, this is a product of two functions, x, y, and then we can separate it into two logs and simplify further. Here's what I mean. Let's subtract ln of x on both sides. So on the left-hand side, we get ln, or natural log of y, minus natural log of x is equal to x to the x, natural log of x. Now we can take log on both sides, which I'll do here. So now we get, I'll do this in separate colors, natural log of, red, natural log of, a lot of colors, natural log of y minus natural log, wow, there's so many natural logs, natural log of x, and then we close this green one, is equal to the natural log or we can separate this into a sum. So this is going to be equal to the natural log of x to the x plus natural log of x, and then we bring this exponent down as a coefficient. So then on the right-hand side, we get x natural log of x plus natural log of x. Just like that. Absolutely beautiful. This is equal to this, essentially, because we could bring that coefficient back into an exponent. So you have x to the x here, and then this multiplies. So yeah, looks neat. And I'll put this in green. I'm not doing those colors again since it took so long. But yeah, let's move forward now. So now that all of our exponents are down to their all of them, there's no x in the exponent anywhere. Now we can differentiate this implicitly. And that's how I like to do it. So implicit differentiation really just means we just solve for dy dx. And here's what that means. When we do ddx of y, this gives us dy dx. And when we do ddx of y squared, for example, this gives us 2y, we differentiate normally, times dy dx. That's how chain rule works. So if we're trying to solve for dy dx, we just have to isolate this term algebraically. And we'll see that in action here. Now, let's differentiate both sides. And remember, the derivative of natural log of x, for example, would be 1 over x. So derivative of ln of f of x is just equal to 1 over f of x times f prime of x. Beautiful. So we can treat everything using chain rule. Let's see what that means. On the left-hand side, let's take the derivative of this giant log. So the derivative of this first would just be the giant log, or 1 over the parameter of the giant log. So then we get 1 over this entire thing, which is natural log of y minus natural log of x, multiplied in the numerator by the derivative of this entire parameter right here. So what's the derivative of this, basically? On the top hand, we have derivative of natural log of y is 1 over ln y, and then chain rule once again, derivative of ln y, which is 1 over y, and chain rule once again, derivative of y is y prime, or dy dx, and then ln, when we take the derivative of the ln of x, same thing, we just do subtract 1 over ln x, and then chain rule, we multiply the derivative of ln x, because this is a parameter essentially. And then derivative of x with respect to x is just 1. So we can write that in. So now we've got the left-hand side all figured out. And we'll see what we can do from there. Now when we're differentiating the right-hand side, it's a little bit tricky. Well, it's not that tricky, actually. What am I saying? So this is just, this is just product rule. We know a derivative of ddx fg is equal to f prime g plus g prime f. So on the right-hand side, we have derivative of x is just 1, ln x, plus derivative of ln x is 1 over x, so we have x over x. And then derivative of ln x right here is just 1 over x. So that's a pretty simple answer. Let's just simplify a little bit. On the left-hand side, we have 1 over y ln y minus 1 over x ln x, and I should write the dy dx actually. We have dy dx minus 1 over x ln x, all over ln of y minus ln of x is equal to ln x plus 1 over x plus 1, just like that. Now all we have to do is just solve for dy dx, and then we'll be done. So we can multiply both sides by this monstrosity on this denominator. So on the left-hand side, we would get, what's happening? All right, 1 over y ln y dy dx minus 1 over x ln x is equal to ln of y minus ln of x. All we did is just multiply both sides by that. This is just algebra. Ln x plus 1 over x plus 1. And then we can simplify further by solving for dy dx. And I'll let you guys do it, but if you want to pause the video, feel free to. But it's just equal to y ln y times, and now this monstrosity, ln of y minus ln of x times ln of x plus 1 over x plus 1, and then we add 1 over x ln x, just like that. So a lot going on here. And if you didn't catch that, essentially we're solving for dy dx by doing implicit differentiation. When we reach a y, we'll eventually get a dy dx because of chain rule. And then we multiply both sides by the denominator, which is essentially what we do in this step. And then what I did a multi-step process, but I just add this on the other side and I multiply by this, so we solve for dy dx algebraically. So we can leave our answer like this, but if you want to write in terms of x, then we go back to the very beginning. We said, I'll copy this, y is equal to x to the x to the x to the x. So therefore, this is the symbol for therefore, dy dx, ladies and gentlemen, is equal to x to the 4. I'll just write this as x to the 4 wherever I see y. So we have x to the 4 ln of x to the 4 multiplied by natural log of x to the 4 minus natural log of x, natural log of x plus 1 over x plus 1 over x ln x. And feel free to keep simplifying. We can even keep going. We can say, because this is just so much going on here, we have, if you really look at these two terms, what's happening? We have x to the 4 and then ln of x to the x to the x to the x. And we can bring this down as a coefficient. So we have x to the 4, or x tetration 4. Then we have x tetration 3, really, ln of x. But what is this to? So if we look at that, that's just x to the x to the x to the x multiplied by x to the x to the x. Now, using properties of exponents, this is just, we have the same base, so we can add these two exponents. That's actually pretty crazy, but if we look at that, what do we have? We have x, and right here, what is this equal to? This is just x tetration 3. That's x tetration 3, and this is x tetration 2. So we just have this. That's what it's equal to. So it's pretty insane, but we have dy dx is equal to x to the x tetration 3 plus x tetration 2 ln of x, all multiplied by, and this is a little bit tricky as well, but we have ln of x to the x to the x to the x. We can take this down and bring this as a parameter as well. We have ln of x to the x to the x. Wow. Ln of x. And this is just equal to ln of x to the x to the x plus ln of x. Because remember our properties. Then we can keep going. We have x to the x, ln x plus ln of x. Insane. So we can write this. Furthermore, we have ln of, what happened here? Wow, so much going on. We got this part done. We wrote this part right here. Then we're just writing this part right here. We have ln of x tetration 4, and we said that's equal to this. So we just have x tetration 2, which is what this is, times ln of x plus ln of x. So this is addition, it's fine. And then we have minus ln of x. So we see a very handy cancellation here. We see cancel, and we'll simplify further. And then here we just can write out whatever else we have. And I switch colors, but I'll fix that in a second. ln x plus 1 over x plus 1 over x ln x. So ladies and gentlemen, if you stuck with me till the end of this video, dy dx is equal to x to the power of x tetration 3 plus x tetration 2, all in the exponent, times ln of x, all times x tetration 2. Yeah, x tetration 2, ln x times ln of x plus 1 over x plus 1. Actually insane. Am I missing something here? I might be, because our parentheses are not aligning properly. Let's see here. Maybe we're missing something. I think we are. I think right here we're missing a parenthesis. That makes more sense. So that means that we need this parenthesis here. And then we get this plus 1 over x ln x. And if you want, you can keep going. It's just fun, so I'll just keep going briefly with the time I have remaining. Then we just do this. We can distribute all of this out. It becomes pretty insane. But if we distribute this here, then ln x times ln of x here, it becomes kind of complicated, but we can distribute like this. Ooh, wow. Wow, okay. So let's first distribute these two terms. We have ln of x all times x tetration 2. I'm multiplying this term right here. So x tetration 2, ln squared x. Then we multiply these terms, plus, and we have x to the x over x to the x ln x, which is what x tetration 2 is. Ln x, that comes here, all over x plus x tetration 2 ln x. And you'll see why I wrote it like this in just a second. But x tetration 2 ln of x plus 1 over x ln x. So this is equal to x to the x tetration 3 plus x tetration 2 of ln x plus x tetration 2. Wowza. So we can even write this furthermore as such. If we have x tetration 2, that's just equal to x to the x, and we're multiplying this entire term by x tetration 2, so we can add the exponents once again. So in the exponent here, we just add another x, and then we have ln, we would think ln of x, but since we're multiplying these two terms by the distributive property, we get ln cubed of x, and then we want to multiply this entire term again by here. Then we would just get this again, x to the x tetration 3 plus x tetration 2 of ln of x. But since we have an ln here, this would be ln squared of x. And this x and this x to the x, that becomes just x to the x minus 1. And since this x minus 1 is here, we can add that to the exponent of our tetration thing here. So you can feel free to pause the video because I'm going kind of fast. This is a little bit more complicated, but this is what we're kind of left with, and then we have to distribute to the last property, to the last term, I mean. Then we can distribute this once again here. Oh, there's one more term as well. But then we get x to the x tetration 3 plus x tetration 2. And then we get, since we have x tetration 2 again, when we put that in our, oh yeah, that's fine, x tetration 2 plus x, and then we get ln squared of x once again, ln squared of x, and we finish this term as well, and then we just have this term remaining. And then we finally add x to the x tetration 3 plus x tetration 2, and since we have x in the denominator, that's x to the minus 1, we can just subtract 1 right here, and then we get, and then we do ln x all over ln x, and the ln x and ln x cancel. This one and this one, they cancel. So we have a pretty hefty term, and it's pretty insane if you look at it. And I've probably made a mistake somewhere because it's so many terms going on. But you can probably factor this out. We have this term here, and I don't think I missed a term here, but maybe I did. We essentially get the following. We get x to the x tetration 3 plus x tetration 2 plus x, and then ln squared x, that factors, ln of x, because that's where that ln comes in, and then what do we get here when we're distributing this to get this? X to the minus, well, plus 1 over x, because that's x to the minus 1, and when we multiply that out, we get that minus 1, which goes over there. And then for here, we have, that's completely fine, so we add 1. And then right here, what do we have to subtract from here? We get plus x to the negative x minus 1. Because when we multiply this out, then we subtract that x, and then we subtract 1, getting us this term. And if we want to rewrite that even, we have, that's just x to the negative x plus 1, which is just 1 over x to the x plus 1. Ladies and gentlemen, this is our answer. I'm sure I've made a mistake. If you want to see the general answer, where it's probably correct, hopefully, it's right here. This is dy dx. But if you want to see the very, very overly simplified answer, we have x to the x tetration 3 plus x tetration 2 plus x, all in the exponent, all times ln squared x times, all times ln of x plus 1 over x plus 1 plus 1 over x to the x plus 1 to the exponent of the denominator. I hope you enjoyed today's video. Let me know if I made a mistake, which I probably did here. And if you have any questions, let me know. See you guys. Thank you.